Thank you very much. Would like to thank Professor Abdollah Khodadoust and as well as the Mr. Chairman, the Brazilian Academy of Sciences, for extending the invitation. It is an honor for me to be here. By way of background, I was born, I won't tell you how many years ago, many years ago, in Shiraz in Iran. And ever since I was a kid, I either wanted to fly them or build them. And many years later, coming out to the United States, the opportunities for somebody with an Iranian background to study aeronautical engineering and build airplanes and be in the field of aerospace was very limited. In fact, I still remember as a student, one of the recruiters from McDonnell Douglas from St. Louis directly pointed to me and said that there is really no future for you in aerospace. Why don't you go into something like computers? And I was, since early ages, very, very passionate about the subject. So my message to you, especially for the students here, is twofold. Is that you're passionate about aerospace engineering, you like airplanes, you like aeronautics, stick with it. Pursue your dreams. You owe that to yourself. At the same time, recognize you're at a very, very wonderful environment in an academic institution that is world-class in Brazil. So you're making connections. Most of your advisors and your friends will remain your colleagues and friends for the rest of your lives. And you're going to learn a very, very interesting subject in the field of aerodynamics and the field of aerospace engineering. But more importantly, you're going to learn how to learn. Learning how to learn. That's a gift that you're giving to yourself that you will take for the rest of your life. Enjoy yourself right now. I know it might be difficult. It's in the middle of classes. I understand this is during the finals. But there really is enjoyment in what you're doing. So many years later, I find myself to be the head of aerodynamics at Boeing's R&D division. My group comprises of about 65 engineers across St. Louis, the Puget Sound, Seattle, as well as in Southern California. One of the areas that we're working is in the area of aircraft icing. So today I want to share with you what is it that we do in a day with regards to aircraft icing at Boeing. Okay, so the subject of my talk today, why is aerodynamics important in aircraft icing? Aircraft icing comprises of many, many different aspects. As Professor Ludig just pointed to today, there are multiple elements that come together in order to make an airplane safe in flying in an icing environment. We'll call it an adverse weather environment. However, in my opinion, not just because I'm an aerodynamicist, but in reality, I think aerodynamics forms the basis of understanding what the issue is and how you can prevent the airplane in getting into a situation that is not recoverable. So I'll tell you a little bit about the historical work that we've done at Boeing. The two areas that I've focused on, one is in the area of high lift aerodynamics, and the other one is what we call the in-spar, frost, or ice. High lift aerodynamics, because the criticality of ice formations and the issues that deal with aircraft icing are critical in two key phases of flight. One is when the airplane is taking off, and the other one is when the airplane is landing, when the airplane is in a high lift mode. Very close to the ground, you have a sink rate, things of that nature. The amount of time that the pilot has for recovery is somewhat limited. And also, when the airplane is in the high lift mode, it is flying in a range or in an area that it really was not heavily meant to do. The airplane is predominantly designed to fly in cruise configuration at 35,000 feet at about 500 miles an hour. So when you're flying really slow, close to the ground, typically that's when icing also happens. In-spar, frost, and ice, it kind of gives you an idea what are the kinds of situations that an airplane can run into. I will finish the talk by going over our current activity in the three different areas. One is rotorcraft icing, followed by what I call swept wing icing, because that deals with transport airplanes. And the last topic is a trajectory analysis tool that Boeing has developed that came out of all the areas, spacecraft icing. Did you know that there is an issue associated with spacecraft icing? So we'll go over that as well. Okay. So why is aerodynamics important in icing? These are representative charts that I actually pulled out of my dissertation from about 20 years ago. There is no numbers on the charts, but you can see the difference in the graphs. For example, the one that shows the lift coefficient, followed the one to the right of it that shows the drag coefficient, and the one on the bottom that shows essentially the airplane response for pitching moment. And essentially, when you have an uncontaminated surface, the airplane exhibits a certain kind of a performance characteristic in terms of its lift versus angle of attack. Same thing with its drag, same thing with its pitching moment. These are just examples. There are other elements, but these are just the key examples: lift, drag, and pitching moment. And essentially, you can see notionally here I've shown that with contamination, whether it's in the form of roughness or it's in the form of a large protrusion, and I'll show you pictures of that here in a minute, that the change in performance, usually reduction in performance, can be drastic, both in terms of a reduction in maximum lift and reduction in the stall angle, but at the same time also in the lift curve slope. These are all very critical parameters that impact the airplane's performance. Same thing with the increase in drag, as well as adverse change in the pitching moment. So understanding these potential adverse impacts is really critical, not just for the aircraft designer, if you're trying to design an airplane that is going to fly in all weather conditions, but also for the operator, equally important for both sides. So I was looking at historical data, digging up historical pictures. How far back can I go and find work being done in aircraft icing? And these two next charts essentially shows you pictures that, the first one here is a old DC-2, I think it is, back in the 1940s, where this work was done in combination or in collaboration between McDonnell Douglas, which is a former arm of the Boeing company, and NASA. At the time it was called NACA. And in this test, they mounted a cylinder, rotating cylinder on the fuselage of the airplane. Through this measurement here, essentially, they're trying to document what the size of droplets are as you fly through an icing condition. And the material that I extracted out of American Society of Mechanical Engineers publication dates back to a New York Times article in 1931, which essentially is referring to, look, if we're trying to make general aviation available to everybody, not just, you know, from 8 a.m. to 4 p.m., not just in days when the temperature is 75 degrees on the ground and sunny. If you're trying to do that, we really have to lick some serious problems, and one of them is icing. And these guys recognized that in New York Times, at the time, was arguably the most important publication in the country, and they listed it there. This is a picture that I dug up from one of the old Boeing archives, and some of you who are really good at recognizing airplanes, you'll probably recognize this is a Boeing 707, right? The only airplane that has a needle coming out of it from this side. And these measurements essentially were made back in 1962 in coordination with the Federal Aviation Administration and the Boeing company, where they're putting simulated ice shapes that were manufactured or generated artificially, and they're being mounted on the vertical tail here in order to fly with that simulated ice shape and determine, can the airplane's flying qualities and handling and control, are they acceptable from a piloting perspective as well as a safety perspective. Okay. Now, Boeing Company is the largest private operator of wind tunnels. Just in the country of the United States alone, we have extensive facilities for testing in Philadelphia, in St. Louis, as well as in Seattle. One key wind tunnel where Boeing is involved in the assessment of icing issues for both its existing airplanes as well as the next generation airplanes is called the Boeing Research Aerodynamic Icing Tunnel, the BRAIT. And this picture essentially shows a section of a fuselage, or excuse me, a section of a wing, aircraft wing, where test of relevant or representative icing conditions is taking place. This wind tunnel is located in Seattle. It is in use almost constantly. I am, of course, very much interested in seeing the icing tunnel that is going to be inaugurated tomorrow and explore possibilities if there's any work that Boeing and Brazil can do together in the icing facility, which apparently is the first one in the southern hemisphere. As far as background of icing work goes, this is a publication that I published along with my co-author about 10 years ago. And essentially it encompasses all of the relevant historical research that has been done at Boeing and at McDonnell Douglas. It's a 100-page review article that we worked on. Took me about 5 years to do this, longer than my dissertation. But it was well worth it because I think we covered just about every area of relevance to the effect of ice secretions on aircraft aerodynamics. We covered aerodynamic simulation considerations, effect of ice on a range of typical type environments, like initial, what we call roughness type environments, run back and ridge ice, which is something that you get, for example, if you run into SLD conditions. SLDs, the short-term known for supercooled large drops, as well as if you have what is known as partially evaporative conditions. If the leading edge thermal anti-ice system does not fully evaporate the amount of liquid that deposits on the flight surfaces, that liquid will run back and essentially refreeze downstream of the heated surfaces. So it is very important to understand what the aerodynamic effect of these large protuberances are on the performance of your airplane. Just as important are large in-flight accretions. For some reason, the air traffic control puts the airplane in a 45-minute hold condition, let's say in somewhere in Europe or somewhere in the vicinity of Chicago, for example, where typical icing conditions are prevalent. And so you really need to understand, or we need to, the designer needs to understand what happens if you get into that situation and for some reason your airplane is not able to handle the icing situation. And last but not least is the ground frost. Ground frost is exactly that. Your airplane is parked on the ground, and because of the moisture conditions overnight, for example, you do end up with residual frost accumulation in the morning. And how do you deal with that if you choose for some reason not to address that or clean the airplane before you take off? Understanding these performance effects are really critical because at the end of the day, it all goes back really to what Professor Ludig mentioned, is that you want to avoid having accidents, first and foremost, especially related to adverse weather conditions. But just as importantly, if an accident does happen, you want to make sure you understand why the accident happened to prevent it from ever happening again. So if you do get a chance, this article is available through a PDF and is downloadable. It's 99 pages, so it might take a while to read, but I think if you're interested in icing, this is probably a good area for you to work on as a background, as a primer. So the two areas that I decided to concentrate on, one is on area of high lift aerodynamics, and the first one, high lift aerodynamics, is shown here in this picture. This is work that we were involved in roughly, you would say, about 20 years ago. High lift aerodynamics is very important for an aircraft designer. You really have to understand how the airplane operates in close proximity to the ground, whether if you're landing or whether you're taking off. So this was a program that we worked on at Boeing in coordination with NASA. So the picture that you see there in the center is what is called the Icing Research Tunnel in Cleveland, Ohio, otherwise known as the IRT at NASA Glenn. It is the largest icing tunnel in the world. So if you absolutely have to have the largest scale model, you have to go to that facility for ground testing. And what you see there next to the test engineer that is sitting in the test section is a high lift airfoil. From that angle, it's difficult to see, but essentially it is a 3-element airfoil that essentially that has a main element along with a back element, which is called a flap, and it has a forward element, which is called a slat. Most of modern-day airplanes, Embraer, Boeing, Airbus airplanes essentially have a very elegant high-lift system that comprises of three elements: a leading edge, and a trailing edge, and a flap. Understanding the aerodynamics that makes this high-lift system work is critical. And one of the first things that you realize when you work on a system like this is that it is very, very Reynolds number sensitive. So everybody here, I'm assuming, understands what Reynolds number is. It's one of the key parameters that you have to understand if you're getting into aerospace engineering. First one is Reynolds number, the second one is Mach number. So the performance of the high-lift system is very, very dependent on what we call confluent boundary layers. There are multiple boundary layers that are present on this type of a complex system. And maybe I'll advance to the next chart, which I think has got a better picture. Yep. And essentially, you have a wake that is coming off of the slat. You have a wake that is coming off of the trailing edge of the main element. And then you have a wake that is coming off of the flap. And all of these merging shear layers are very, very complex to predict. It's not like a simple boundary layer that is coming off of the flat plate. And the way the high-lift system develops its max lift performance capability is because of how you place the leading edge and the trailing edge in close proximity to the main element. These gaps are critical for the performance of the airplane. And that's why it was very important for us to understand what happens in an environment where you start to accumulate ice on these elements, and the ice essentially starts to impact those gaps that have been optimized for performance close to the ground. So this picture here shows a series of tests that were done at different flight conditions, representative of takeoff, representative of landing, representative of what we call hold conditions, representative of your thermal anti-ice might have gone inactive, things of that nature. So we accumulated a large database of ice accumulations in the Icing Research Tunnel, and we took select ones because these tests are very expensive. We have to be very selective in terms of which ones we pick, but we picked a select few and manufactured them out of material that we could take into a high-pressure tunnel and simulate the environments that are representative of a large transport airplane. What we ended up doing was that we took these ice shapes into the NASA Langley LTPT, which is called the Low Turbulence Pressure Tunnel, the LTPT, and tested them at flight scale conditions. Again, because of the confluent boundary layer, accurate simulation of the Reynolds number, flight Reynolds number, is critical. In other words, with a high-lift system like this, if this high-lift system is meant to operate on a Boeing or an Airbus or an Embraer that wants to fly at about 35,000 feet, and its typical approach condition is about 200 knots, you're talking about Reynolds numbers that are on the order of 30 to 40 million. So everybody knows how to calculate a Reynolds number. And you can quickly imagine what you need to do in order to calculate the Reynolds number when you're in a low-speed tunnel. And that's one of the reasons why we increase the pressure in some of the tunnels. That's why we call it a pressurized facility. By increasing pressure, you're directly increasing density as a part of the state equation of the state. And by increasing the density, then you can increase the Reynolds number significantly. What that really translates to is that I cannot test this kind of a airplane or this kind of an airfoil in a low-speed tunnel and make the assumption that the results I get in that tunnel is going to be representative of flight scale conditions. And this is critical for a transport airplane designer. You have to understand what the flow field is. You have to understand the aerodynamics in order to design for these critical safety conditions. So we did this in the LTPT wind tunnel, and we used some representative ice shapes for the leading edge of each one of the elements. And essentially what this chart here shows you is the increment in the maximum lift. So CL max is very important for airplane design. Maximum lift is critical. Why is it important? Because it ties directly into your approach speed. It ties into your takeoff speed. You have to have a very solid understanding of what the max lift performance of your high lift system is. And any loss in that high lift system, any loss of performance, especially in CL max, translates to drastic changes, potentially drastic changes in approach speeds and takeoff speeds. And these are critical for the airplane performance. The pilot needs to be aware of this, or I, as a designer, have to build that into the flight control system. So when the pilot switches on the icing conditions or icing environments, the flight controls automatically revert to the airplane mode in an icing condition. So the two key messages to take away from this plot are summarized here. There are significant performance losses, both in lift and in maximum lift, in drag, as well as what we call the stall margin. Stall margin is when your alpha stall angle of attack changes drastically. That's called the stall margin. So you can see from the plot there's changes across the Reynolds number range, and the horizontal axis, that's the Reynolds number. And so when you get up to about 16 to 20 million Reynolds number, that is starting to represent large transport airplane conditions. So there are changes going across. If there was no changes, you would expect these lines to be absolutely flat. And also there's some drastic loss, as you can see. And in the case, this worst case essentially shows that all three elements where slat, main, and flap had ice shapes on them, and the ice shapes were simulated with the roughness that we observed in the actual wind tunnel test at NASA Glenn. Okay, another topic that we had to investigate, this one is back in maybe about 20 years ago, is what is called the in-spar frost, under-wing frost. And essentially the reason for this type of ice formation is that you take a wing of an airplane. In this case, this is a 767 that was parked in Frankfurt. You just landed after flying, let's say, at about 35,000 feet. Just as a rule of thumb, if your temperature on the ground is, say, on the order of about 70 degrees, 75 degrees Fahrenheit, and my apologies, what would the Celsius be? About 25 degrees Celsius, probably, roughly. At 35,000 feet, you're potentially at minus 60 degree Fahrenheit, which is maybe about minus 40 degrees Celsius. So that temperature, very low temperature, starts to impact the aircraft. Both the skin is going to be very cold, and just about everything that is not insulated will be very, very cold. Well, guess where the fuel is stored in the airplane? It's usually stored in the wings. This is the front spar of the wing. You can see the engine. This is the leading edge. The front spar of the wing is out here, and the aft spar of the wing is typically somewhere just upstream of the control surfaces. Well, that cold-soaked fuel, the fuel that is turned very, very cold as a result of flying at very high altitudes, when you land, let's say you land in Rio on a nice, beautiful day where humidity is maybe, on the order of 80%, and the moisture conditions are just right, that cold fuel will force the aircraft skin to go into a condensation mode. Just about all of the humidity that's in the air will start to condense on the aircraft surfaces. Part of that is in close proximity to the fuel tank, which acts as a major heat sink because of all the fuel that remains in the fuel tank, starts to condense that moisture condensation, and that's where you get what is called in-spar frost, or in-spar ice. And the occurrence of this has become so common that both the FAA and before EASA, it was called the JAA, they became very interested in what's the performance effect or impact. Because this airplane lands, and typically when airplanes land, after about maybe a 1 or 2 hour flight, they're not done for the day. There's still fuel in it. They will take about 1 hour, deboard the passengers, take all the trash out, bring new passengers on board, put in brand new food, fresh food, clean up the toilets, get it ready, and head back out again. So what can you do? Do you really have to get rid of this stuff onto the wing before you take off again? It's critical. We have to understand that far better than we did. So about 20 years ago, we mounted a campaign with Boeing and McDonnell Douglas and FAA to fully understand what the effect is. And aerodynamics, again, plays a huge role here. In aerodynamics, we have a terminology, we have a phenomenon, it's called the stagnation line. And it turns out, and I'll show you results in the next chart, it turns out that so long as the stagnation line is upstream of this frost formation, the impact of the frost on drag and lift are minimal, literally minimal. And those results are shown, again, with the wind tunnel test that we did at the LTPT, low turbulence pressure tunnel. We took an airfoil that was representative of takeoff conditions. Boeing airplanes typically have their leading edges sealed, so you can see that in a sealed slat type configuration. Some other airplanes, I think some Airbus configurations, take off and land with what we call a gapped leading edge configuration, and that's shown up here. And we tested that in the low turbulence pressure tunnel, this configuration, and you can essentially see that the impact to the max lift degradation as well as the star margin degradation is minimal. And this gave us assurance that this type of a meteorological phenomenon is not a hindrance to aircraft operations. Okay, so let's see. I want to switch now to some of our current work. And the current work, first I'll touch on rotorcraft icing, then I'll switch back to the transport airplane icing, and we'll finish off with the spacecraft icing. Rotorcraft icing, essentially, what is listed on this chart, you might see is truly representative of the challenges that we have in the world of aircraft icing, predicting ice-shaped formations. Characteristic lengths in any kind of an engineering problem, characteristic lengths, characteristic time, understanding that is very, very important. The problem becomes complex if you have multiple time scales and multiple length scales in any kind of a flow field. In this case, in terms of a rotorcraft, you have a blade that is hovering at multiple frames per second. That's a time scale that is very different than the time scale that it takes for ice to form on an aircraft or in flight surfaces. Same thing with the characteristic lengths. Characteristic length is very important because it goes into the Reynolds number calculations and considerations for airplane design. For a rotor blade, it's on the order of feet, meters, similar for airplanes. Whereas the characteristic length in ice formation is typically on the order of microns or very, very small. So it's very difficult to use first principles, distant time to formulate the icing problem and really try to characterize it well. That is one of the reasons why since the 1930s, the icing problem to this day still remains a challenge. And we have to do a lot of testing, both flight testing and ground testing, to make sure that the airplane is safe. From a designer perspective, my ultimate goal is that we can do all of the simulations in a computer, because that means that we can do it efficiently. And with testing, whether you're doing ground test or flight test, there's always a chance that something may go wrong. That's not a good thing. But in a computer, I can make all the mistakes I want to and learn from it. But we're still, in the area of icing, we are far from being there. But that's the push. We eventually want to get there. So how do you get there is a better understanding of the physics of ice formation. And that's really where one of the areas where I think the next generation of engineers and scientists can really help us. So in the area of aircraft icing, Boeing has been involved in a consortium. What you see there in terms of the logos down there is, obviously Boeing and NASA, Bell Helicopter, Sikorsky Aircraft. The little B that you see there is Georgia Tech. Georgia Institute of Technology is a major center for rotorcraft research, academic center for rotorcraft research in the United States, so we're partnered with them. And we're looking at various areas, rotorcraft, rotor and fuselage ice accumulation, shedding from rotating and an oscillating blade. These are two key elements for rotorcraft design, are very critical because of the very strong centrifugal forces. You may shed ice that may become a projectile. And ice, anybody who's picked up a piece of ice, you know how hard it is, and it can really be a detriment to performance. And of course, just as importantly, you want to understand what the de-icing and anti-icing system performances are. And also, really the key thing from a design perspective is that what is the impact due to the accumulation of ice on rotor surfaces? Again, you might say, replace the word rotor with a transport aircraft, regular aircraft. Equally valid. So testing has been done by our Rotorcraft community at the Boeing company. Again, our primary testing facility is at the NASA Glenn Icing Research Facility because of its size. Tests have been done in 2010 and 2013 to really accumulate a large database of ice accretions to compare against the emerging prediction methods. This chart essentially shows how testing at Boeing is done in partnership with both NASA as well as the consortium, which is listed there in the lower right-hand corner. NRTC stands for National Rotorcraft Technology Consortium. And you can see that Boeing gets involved with a variety of different government agencies as well as industry in order to solve this complex problem. Now again, as Boeing is expanding its relationship with the government of Brazil and we're expanding our infrastructure in the country, this is potentially an area that we need to look at for future collaboration. Role of CFD. CFD stands for Computational Fluid Dynamics. Is critical for us in many areas, in aircraft design and in rotorcraft design. This picture here shows a tool that we use very, very heavily. It's called Overflow. Overflow is a simulation that takes advantage of what is called the Reynolds average, Navier-Stokes form, RANS, on a structured grid type technology to predict the aerodynamic characteristics of a flight vehicle. In this case, it is a rotorcraft. It is coupled with what we call an ice prediction method. It's called LEWICE. LEWICE essentially is Lewis Ice Accretion Code. Back before NASA Glenn was called NASA Glenn, it was called NASA Lewis. And the tool was developed at NASA Lewis, and it's called LEWICE. Very heavy workhorse for us. Just about all of the industry understands it and uses it for ice accretion methods. So this picture essentially shows the kind of simulations that we've done using LEWICE on a rotorcraft type environment. Now, I mentioned the role of CFD, and the chart that you're looking at Boeing, typically these are called walk-around charts because it's like an airplane, and as if you're walking around an airplane, maybe putting on your Google glasses that essentially has the information in front of you. Any part of the airplane that you look at, in this case, is showing what has been the role of CFD, computational fluid dynamics, in developing, and in this case, it's the next generation Boeing airplane, the Dreamliner 787. And on top of the chart, essentially, you'll see the colorations that show where CFD has been used, all the way from heavily to some limited utilization. And in the middle of that picture, on the starboard wing, you'll notice that icing is highlighted there. And we have done some CFD utilization, some use of computational fluid dynamics in order to model what kind of ice formations can we expect. But again, as I pointed out, this is such a complex area of physics that, that is difficult to do all of that in CFD. So we end up doing the initial predictions in CFD and then take those predictions into a wind tunnel test and also into a flight test and validate that, the airplane's performance that way. So, generating ice shapes computationally. Why is it important? When I look back at the historical literature, the way Boeing and McDonnell Douglas and other companies have generated ice shapes has been with a lot of difficulty. You have to go into a flight test facility or a ground test facility like the icing tunnel in Cleveland or the icing tunnel at Boeing. First grow the ice shape, then you have to take a mold of that. And usually taking a mold is a very heat-intensive procedure. So in the process, you're melting the ice. So the question is, how do you, with some level of fidelity, capture all the important features in the ice shape? And it's very difficult to do. That's where the computational methods come in. And LEWICE 3D, again, is a code that was developed by NASA greatly reduces the need for us to interpolate or even extrapolate ice shapes to generate wind tunnel model parts. And of course, the technical challenges here are, and here's a message again for all the students that are in the room. Whether you're using a wind tunnel or you're using computational methods, you have to understand your tool. What that means is that you need to know what its capabilities are, and you also need to know what its limitations are. You can't just say, my God, I've got this tool right here that will do everything. This will do everything. Not true. You need to know what its limitations are, because you're designing something that eventually is going to have people flying on it. You don't know who those people are. It might be your mother, it might be your aunt, it might be your husband, it might be your daughter. You want that airplane to be as safe as possible. So you need to respect the limitations of the tools. And one of the limitations of LuICE 3D right now is that in as much as it does do a very good job in calculation of the droplet efficiency distribution, and it does a really good job in determining what the limits of the impingement are, those calculations are incredibly time intensive, very time intensive. So keep that in mind. I'll come back to that later with the spacecraft icing in a few charts. So finding, also, just as importantly, finding sufficient experimental data is just not possible for us. Again, because doing these types of tests are very expensive. They take a lot of time, they take a lot of resources. So that's why the drive to try to computerize the models, computerize the methods as much as possible. Remember though, in English we have a terminology called GIGO, G-I-G-O, garbage in, garbage out. So we have to be very careful in terms of what we put into the models. You have to understand the physics, you have to understand the flow field, very, very critical. So what we're trying to do with LuICE is identify what the flight conditions are that are considered critical for airframe icing. And then we use what we call Navier-Stokes solvers. And the two primary tools that we use at Boeing are Overflow or CFD++. And these are basically run with these conditions that have been identified to generate flow fields for input into LuICE 3D. LuICE 3D then generates collection efficiency and ice shape cuts. On the lower left hand, you'll see the collection efficiency that has been calculated by LuICE on a 787 type configuration. And on the right side, there are the predicted ice shapes span-wise. So what you're getting is both a representation of the ice shape, and you're also getting the limits that the tool is predicting you're going to collect ice for any particular environment. What that tells us, from a design perspective, how far back on the airplane do we need to protect the leading edges, the aerodynamic surfaces. The ice shapes will tell us what do we need to go in flight test and wind tunnel test to really assess what the performance losses are. So from an aerodynamic perspective, our goals for icing are, ultimate desire is to eliminate icing tunnel testing for developing or generating ice shapes for aerodynamic analysis. I think we're probably still about 20 years away from doing that. But that is a desire. We need to continually work at it. And we want to streamline the icing process because, again, Boeing takes considerable measures in determining what the environment is, what the flight environment of the aircraft is going to operate. Again, we're not in the business of developing airplanes that will fly from 8 a.m. to 5 p.m. on a nice, beautiful, sunny day, where the probability of running into adverse conditions are minimal. Your airplane really needs to be able to fly in all kinds of conditions. And just as importantly, we want to improve the effectiveness of the entire process and ensure that the critical features in the ice growth calculations are captured. So LuICE 3D is the workforce for us, and this is the current Boeing ice accretion modeling tool. It captures all the 3D icing information that we believe is of relevance, impingement limits, water catch, and some of the shape characteristics. This is really where the weakness is, some of the shape characteristics. And it is that shape that becomes an aerodynamic issue for us. The two first elements are really important. Impingement limits, again, allows us to know how far back we need to protect the surfaces. Water catch, that's the amount of water as a function of time that we think is going to land on the aircraft surfaces. What that does for the designer is that how many BTUs, how much heat do you have to apply, either in the form of electrical energy or offload from the engine heat, you have to put into the leading edges or into the aerodynamic surfaces to keep them clean. Two very important areas. The third important area is, what is that shape? The shape that grows as a result of accumulation of water, and if it is left untreated, if the thermal anti-ice system is not operating for some reason, if it's broken in flight, things happen, what would happen? What is that shape going to look like, and what is its impact on aerodynamics or the overall performance of the airplane? That's the part that low ice is still weak and forces us to go into a wind tunnel and eventually into a flight test. Again, very, very expensive endeavors, but critical for us to do because we need to know what the safety of the airplane is. Low ice allows us to do rapid generation of ice shapes for the Appendix C icing envelope. And again, just as I was pointing out, we can't really use the tools as a black box. Know your tool. We have to understand what the limitations and what the capabilities of just about any tool are. So that's a broad message, and here specifically with regards to using the icing tools. So going forward, as we contemplate on doing collaborative research, let's say with COPA, with UFRJ, or with other entities in Brazil, it is becoming more and more difficult for Boeing to share what is called its real specific geometry. Next generation 777 or 787, that's just the environment we live in. So the question is, if we can't use something that is very specific to Boeing, or something that's very, very specific to Embraer, or something that's very specific to Airbus, what can we use? Absence those options, what we have come up with in partnership with NASA is design what is called a Common Research Model, CRM, that is a generic geometry. Boeing designed this configuration, which essentially, when you look at it, is representative of a modern transport airplane. If I didn't tell you this thing was a generic geometry, it would be very easy to really think that this is a representative 777 or Airbus 350 type configuration. So it has all of the features of a modern airplane, representative, but we made it generic and released it publicly, so that this way the whole world can use this geometry and be able to do calculations, whether it's aerodynamic calculations or icing calculations. Common Research Model is designed by Boeing. It was a baseline for CFD drag prediction workshop. Some of you guys might be familiar with the drag prediction workshop that American Institute of Aeronautics and Astronautics holds on a regular basis. And it represents a typical wide-body airplane. Here are some performance charts for some of you guys who are into aerodynamics. You will appreciate this. These are pressure plots that are taken across different areas of the wing, all the way from the lower left-hand corner, which is the inboard section of the wing. You kind of walk up to the midsection, as well as then, on the right-hand side, you finish up by going from the mid-span all the way out to the outer span. And you can see that the pressures are very, very representative of what you would find on a Boeing or Airbus type airplane, where you have a supercritical wing, and what you see in the pressure contour that's on the wing planform, you'll see a mild shock that sits at roughly about 60% chord, followed by pressure recovery to atmospheric pressure. This is, again, a sign of a well-designed wing. What happens if you put an engine and a pylon on this wing? And that's essentially shown on this chart with the dashed lines. And when we put an engine and a pylon on it, it represented and behaved exactly as we would expect a large transport like a 777 or an Airbus 350 behave. So this kind of a configuration really has become a generic test bed for validation of what I would call not just for icing, but emerging CFD prediction methods. The contours that you see on here are essentially representative of the CFD calculations that have been done, not just at Boeing, but a variety of interested parties in this configuration, both for the unengined as well as the engine configuration. The groups that have so far expressed interest in Common Research Model are folks at the Drag Prediction Workshop, COMSAC stands for Computational Methods for Stability and Control Analysis. Various wind tunnel facilities have expressed interest and are also in the process of building a wind tunnel model of the configuration to be able to test it aerodynamically. National Transonic Facility at NASA Langley, the NASA Ames 11-foot tunnel, both of those are transonic facilities. JAXA, which is the Japan's version of NASA, and in Europe it's the European Transonic Wind Tunnel, are in the process of building models of this configuration. Large cross-section of the government and industry have also expressed interest. The U.S. Air Force, Boeing, multiple other industry representatives or members, Gulfstream, Cessna, Lockheed Martin, Northrop Grumman, Pratt & Whitney from an engine perspective, and of course government agencies like NASA, Air Force, and the Navy. And just as importantly, we have just started to use the NASA Common Research Model for a swept wing icing project that NASA awarded to Boeing and team members as what they call an NRA, NASA National Research Announcement. So what are we trying to do in this study? The larger airplanes have typically very large leading edges, and a challenge is how do you simulate? How do you simulate the ice that forms on these extremely large leading edges? If you stand next to an Airbus 380, it will just amaze you. The leading edge is so big that it just baffles the mind how we as humans are able to do the kind of things that we do. So the question is, with regards to icing, how do we simulate? How do we simulate the ice shapes appropriately? And so the purpose of this study really is to develop an approach that is superior to the current methods and determine what the ice shapes are for swept wings. We're using the Common Research Model to evaluate what the ice shape characteristics are at 3 different span stations. One is the inboard, the other one is the outboard, and the middle one is called the midsection. And essentially, the image that you see there on the bottom of the chart is that is a cross-section of the leading edge of the airfoil that has been truncated, and essentially with the truncation, what we intend to do is use a single segment flap to simulate the leading edge pressure distribution and simulate the environment that exists on the flap, on the leading edge of the airfoil. Now, this is something that is somewhat straightforward to do on a wing that has no sweep, but it's a real challenge when the wing has sweep. And that's where the research is now. It's a 3-year phase 1 project, and we're starting to make progress in that area. Any one of you who keeps track of publications in AIAA, look for this publication. Will come out in the next AIAA conference in Atlanta, which is, I think, supposed to start right around the same time as the World Cup. So it's okay if you don't want to pay attention to the AIAA conference and you're paying attention to the World Cup. It's just okay. You can usually pick up the documents immediately afterwards. So I want to finish this discussion with a topic that is maybe a bit odd, you might say. How does a spacecraft form ice? And essentially what you see here is the launch vehicle, the Space Shuttle system, that is now retired, by the way. But essentially what you have is something very similar to what happens in the INSPAR flight, or INSPAR ice, which I showed you a few charts back. In the case of an INSPAR, in this case here, somewhat similar is that you've got liquid fuel sitting in the tank that essentially the launch vehicle is going to use to get up to the low Earth orbit. And in this case, as you can see, quite a few of you, I'm sure, are familiar with what the Space Shuttle looked like. So the orange tank is where the liquid fuel was stored. And the lower section is where the hydrogen is, and in the upper section, close to the radome, which is in the right-hand side picture, is where the oxygen is. And there is some amount of what we call thermal protection system, the TPS. The orange material is intended to provide a certain layer of insulation. But quite obviously, these images show that in certain conditions in Florida at Kennedy Space Center, when this thing is sitting on a launch stack, launch complex, waiting to be launched, in the warm nights and the high humidity, the moisture conditions are just right to form frost and possibly some form of ice on the tank, on what is called the acreage. So this becomes a challenge for us when in that extreme mechanical and thermal stress environment that is a launch environment, when this vehicle is going up, all this material starts to shed and becomes a trajectory, it becomes a projectile. And in fact, one of the things that attributed to the loss of the Space Shuttle Columbia a few years back was not so much as the ice, but something very similar that I'll show you here next. So essentially, what you see there in the middle picture is a computational generation of what we think transpired that led to the accident that doomed Space Shuttle Columbia on re-entry. The accident took place during launch as the vehicle was coming off of the launch complex. A certain amount of foam that essentially is an insulator near the front of the vehicle. The space shuttle, the orbiter, is mounted to the tank using aft fasteners as well as a forward, what we call a bipod. This is the bipod right here. And the bipod has a certain amount of foam around it that essentially is meant to protect those portions of the mounting mechanisms from extreme amounts of heat. So you might say, God, we're talking about foam. How heavy is foam? Well, foam itself is not heavy, but when it's sitting out there on the launch stack for about 10 hours before getting launched, and a lot of moisture is being soaked by that piece of foam, now this foam becomes something like a wet sponge, somewhat heavy. So this foam came off on launch, and it became a projectile. And our calculations did validate that it had the high probability of impacting where it caused a significant amount of penetration to the leading edge of the orbiter. Of course, we did not discover any of this until after the fact, and it was quite tragic. But downstream of that, some very, very strong methodologies were developed to predict this type of an environment and prevent it from happening again, even in a spacecraft environment. Now, America's next generation spacecraft is not going to look like this. It's going to look like the old Apollo. However, we are just at the beginning of commercial space travel. Brazil has a very strong space agency. Many other countries have aspirations on getting into low Earth orbit and beyond. So this type of analysis and understanding is very important for us as aircraft, or I will just say flight vehicle designers. So what we did was use this tool, tool that was developed at NASA Johnson Space Center, and started to work with it. We really found it to be a powerful tool. It doesn't predict ice shapes, obviously, but it gives you trajectory analysis, and it also gives you impingement location. Now, initially, it was developed for projectiles of this nature. You know, these things are about the size of a, trash can, fairly large. So is it possible for us to modify the drag terms and the aerodynamic terms in the code and make it representative of what you would consider to be a water droplet trajectory? And we did that. So we modified the code. Why did we do that? Because it has significantly efficient search algorithms, and this capability really allows us to do trajectory analysis predictions with rapid turnaround, significantly shorter amount of time. So keep this in mind. If you're not interested in generation of ice, if you're just interested in collection efficiency and impingement efficiencies, this would be a powerful tool to use. So we implemented a drag model into this thing for micron-sized water droplets, and we started to test it on a variety of aircraft that Boeing was developing. The one on the lower left-hand side is Boeing 717, which is MD-95, as well as McDonnell Douglas-80. The interest was that if we put an antenna there that you can see with the orange dot on top of the cabin, this is essentially what allows us to get free Wi-Fi inside of the cabin anytime you're flying today. It's become so commonplace that we don't even think about it. But having that bump on the airplane, what does that do to us in the event of in an adverse environment? Just as important is the large, what is called a cargo freighter, large cargo freighter, LCF, which is a modified 747 to carry the large pieces that Boeing is manufacturing in Europe, in Australia, in Asia, how do these pieces get transported to Puget Sound where the final assembly takes place, and that's done through the Dreamliner, the large cargo freighter. Question was, with making that major modification to the 747, really what are you doing to it in an icing environment? So we use this trajectory code to do a first order analysis. Is there even a problem that we need to worry about? If this tool can show us there is a problem, then we're going to go in and look further. And so essentially what we ended up doing was predicted the flight environments on the 717 using a computational fluid dynamics solver called Overflow, and applied the modified debris code to it, and we evaluated the antenna impingement. And this picture here essentially shows you the areas of impingement. We did significant amount of searching to find out where are the water droplets potentially coming from, and this just shows you an example of that. And so you can see that there is going to be impingement to the wing, fully expected. There's going to be impingement to the pylon where the engine attaches to the side of fuselage, again to be expected. There's also impingement to the vertical tail, which we also expect, and we predict for it and we take care of it. Also to the leading edges and so on. But we did not see a significant impact to the radome area. We did the same thing for the MD-80. The results are shown here. Just as importantly, we wanted to see what the water catch distribution is, the collection efficiency. Again, remember, collection efficiency translates to how much water collects as a function of time, and knowing that information is important so that you can translate it to how much heat you need to have on the surfaces to keep them free of any kind of water. So this is an image of the large cargo freighter, and the debris tracing code, the NASA tool, was used to determine if the upper lobe of the fuselage would accrete ice, and also a holding case was selected at about 2.5 degrees as a worst case. Essentially, these show results that are representative of what you will find in the Appendix C, which is the FAA method of determining what the appropriate sizes of water droplets are. And again, we did not see anything that appeared to be significant for us that we needed to do extra treatment beyond what Boeing does today to these types of configurations. So essentially, we've taken a tool that was developed out of spacecraft icing and modified it to apply it to a group of different type of airplane configurations that Boeing operates, all the way from the 717 to the large cargo freighter. And the picture down there shows one of Boeing's concepts for next generation, what is called an ISR platform. So in summary, we've been involved in the field of icing research since the early days of the company. The accumulation of ice on flight surfaces, just as importantly on aerodynamic surfaces, is critical. We fully realize that, and because of that, Boeing spends a tremendous amount of resources, including running an icing wind tunnel almost around the clock every day of the year to fully understand what kind of ice shapes we're looking at and what do we need to do to protect those on the aircraft surfaces. And just as importantly, last but not least, is that Boeing works globally with academia, industry, and the government agencies in a collaborative sense, as well as with rulemaking organizations to help implement what we call analysis-based certification approaches to icing. With that, again, I would like to thank you for your time, and I apologize if I went longer than I should have. Ready to take questions.